I hope my mic, yes, it's working. So welcome everyone, good morning. Today we're here to talk about Azure AD. Just for those who don't know me very shortly, I'm Dirk-jan, I live in the Netherlands. So it's a European conference, it's great to be close to home. I'm, a bit of everything. I do hacking, researching, and since last year I also started my own company. So doing all kind of things security-wise. And I also really like to write tools. So I wrote a couple of tools for Active Directory, but also focusing more on Azure AD tooling. And I really like to write tools to help me in my own research and also just to make things easier for everyone. I write blogs on dirkjanm.io, and I have a Twitter account where I tweet about my new research, my talks, and everything. So what are we going to talk about today? First, I want to give a short introduction about what Azure AD actually is and how Zero Trust looks from the perspective of Microsoft, very short. And then we're really going to diving into Azure AD joint devices, so looking how the device joins works and all the tokens that are in play, how these tokens are protected on the device, how they're protected by hardware and by software. And then dive into the vulnerabilities that I found while researching this. So stealing the tokens, bypassing security measures, and abusing some parts of the join process to do things that weren't quite intended. And lastly, if there's some extra time, also a nice MFA bypass if you have the right admin role in Azure AD. So to clear some things up, this talk is about Azure Active Directory. Despite being called Active Directory, it doesn't really have any relationship with the on-prem Active Directory that we're all probably very familiar with. But Azure AD is really the identity platform for all of Microsoft's cloud offerings, so Office 365, but also the Azure infrastructure. And you can also integrate your own applications with Azure AD so that your users can authenticate to any first or third-party application. In this talk, we won't be talking about Azure infrastructure, such as VMs or databases or whatever, but it's really focusing on the identity part of Azure AD. Now, a little bit about Zero Trust. It's been a popular buzzword from the last few years. I'm not even sure what exactly Zero Trust means or what people envision by it. But this is an image that Microsoft uses. And basically, what the ideas of Zero Trust is that you don't have the traditional firewall-based approach, and when you're in the office, then it's trusted or something, but it's really Zero Trust, anyone can work from anywhere, and whether you can access certain resources is really based on telemetry. So if you're on a trusted corporate device, then you can access some business apps. And if you are on a bring your own device, logging in from, some shady country, then you're not allowed to access sensitive business data. If you look at this picture, on the left-hand side, you see a few things. First is identities. Well, identities is, of course, obvious. It's your account, your personal trusted account, and protected with a password, with MFA, or with passwordless authentication methods. And on the bottom, we also see devices. So in Zero Trust, devices actually play a quite important role. So what this means is that part of your identity lives on your device, and the device checks if it's compliant and if it's running an antivirus or something. And as long as you're on that trusted device and that device doesn't do anything weird that makes it become untrusted, then you can log in to your business apps. And that's really the very short version, and not mentioning all the AI and machine learning things that move into play here. But short version, it's about identities and also about devices. And in this talk, we'll really talk about device identities. So what is a device identity? A device identity is basically a device that is either registered or joined to Azure AD. And that can be a mobile device, so your phone, or it can be Windows 10 based, so it's just a laptop or desktop. And these devices exist as objects in Azure Active Directory. So there's a link between the physical device that I have here and the device as Azure AD knows it. And these devices can then be managed, for example, by a mobile device management solution, or by Intune, which is Microsoft's own device management solution. Now, there are several options for device join. The first one is Azure AD joins. That's really similar to Active Directory domain join. It's for corporate devices, and you're joining it to Azure Active Directory to make sure that Azure Active Directory is the kind of the authority for that device, which pushes all the policies and the identity layer. And that's really for corporate-owned devices. So you're not supposed to do that for like your phone or your bring your own device. And this is primarily for Windows 10 only. So mobile devices, you can also add to Azure AD, but then they are Azure AD registered. So that's a different thing. For Azure AD, there's a difference between registered and joined devices, and it differs a bit in how it treats those devices. There's lastly also a hybrid join. That's if you still have an on-prem Active Directory and you want to integrate that with Azure AD, then your domain joined devices can be synced to Azure Active Directory, and then the device will also register itself in Azure Active Directory using the data from the on-prem device. So device join and compliancy, that's two things that go kind of hand in hand. So really the advantage of, and where this whole zero trust comes into play, is that you join your device to Azure AD, and then you have it managed by an MDM, such as Intune in this case. And in Intune you define certain policies, such that, for example, you need to have a certain endpoint protection installed, your drive needs to be encrypted, kind of like the old GPOs. So you define all kinds of policies that the device needs to comply with. And if the device has applied all the policies, it reports itself as, hey, I did all this stuff, and then the device is treated as compliant. And you can use this with conditional access to specify, like, if you want to exit this resource, you need to be on a compliant device. So that's quite a strict security measure. So if you would set that for an application, then even if I have the password and the MFA token for a user, I still wouldn't be able to sign into that application that has, for example, sensitive business data, because I'm not doing it from a compliant corporate device. And this conditional access policies where a compliant device is needed is really what I'm looking into in this talk. So compliant devices is also kind of linked to corporate-only devices, because like most organizations, they just don't want you to have just any device that you use for corporate stuff. Like if you have a crappy old laptop that you join to the company's Azure AD and then just make that device compliant, then they still don't know what kind of hardware is on there, what was previously on there, and what's on that. So a lot of organizations, they will lock down which devices can actually be considered corporate devices. And then they also make sure that you can only enroll corporate devices into Intune, which is a prerequisite for it to become compliant. And there's a few ways for that. And in this case, we'll be mostly looking at Windows Autopilot. And Windows Autopilot is a technology which allows you to like specify which devices are considered corporate, either when you buy them directly from a vendor or when you pre-register them based on a serial number. So if you're using Autopilot, you can just buy some devices from a hardware vendor, and they like enroll the hardware IDs of these devices in Intune, and then they can be directly shipped to your employees, and it will automatically install all the software. It will automatically join to Azure AD, and that's, well, it's kind of an end-to-end solution, but it's also a way to make sure that only devices that were actually bought by the company can be enrolled and can be used for corporate access. So I'm really looking for this research scenario for kind of the strictest scenario. So it's Windows 10 devices or Windows 11, doesn't really make a difference. So the company is using Autopilot, so you cannot just take any laptop and use it for corporate access. because they restricted personal devices. There's a requirement for device compliancy, so you cannot access any business data from a non-compliant device. And also the device uses hardware-based protection to make sure that the secrets are protected. Now, I had a few research questions for this. First of all, like how are devices actually joined to Azure AD? How does that work? How is there like a sort of trust established between the device and Azure AD? And if there's a trust, it probably relies on some sort of secrets, cryptographic keys or certificates and stuff. How are these actually protected by hardware? And if they are protected by hardware and we're not supposed to access them, can we still extract them, or can we bypass the need for having the actual hardware so we could steal the secrets away and use them somewhere else? And can we bypass the requirements for a compliant device? So to start with the first one, I started looking at the device join flow. So if you have a completely new Windows device, for example, laptop, and you start it up for the first time, during installation, it will ask you to sign in with your Microsoft account. And if that's a corporate account, it will automatically join the device to Azure AD if you enter that here. Alternatively, if you have already installed Windows, then you can still join the device after installation from the settings. So you can go to Access Work or School and then say join to Azure AD. And then you can also sign in with your corporate account and it will be joined to Azure AD. So once you start this flow, it will just request you to sign in. So you have to enter your username, password, and MFA if that's set up. It requests a token for the device registration service, and then it prompts you this final OK prompt, like, are you sure you want to register this device to this organization? And once you click join, then a lot of things start to happen. So first of all, two public-private key pairs are generated. The first one is the device key, and the second one is the transport key. So these are like asymmetric cryptography keys, and the public part of that is sent to Azure AD, so that it can validate your possession of the private part of the key. And of course, the private key remains on the device itself. If you look at the registration request, we see a few things here. So at the top is the authorization token. This is a really standard access token for the device registration service. If you're familiar with Azure AD tokens, this is quite normal. So this is basically the token from your user that you're accessing the device registration service to join this device to Azure AD. The second one is the certificate signing request. So what it actually does is it created a signing request and it sends that to Azure AD so that Azure AD can issue a certificate for the device. There's also the transport key, and this is the public transport key, and the transport key is used later for some additional encryption. Then there are also the device properties. So it says what is the type, what is the OS version. That will also be used in the registration, but it's not actually validated. It's just to populate some informational fields in Azure AD. Then there's the join type. We're only interested in join type 0 here, which is used for AAD join. For device registration, there's another join type, so that's actually using the same flow, but with a different number here. And there's also this device ticket, which you can leave out, but we'll actually be looking at what exactly that device ticket does later. So this is just a post request that you send to Azure AD, and then it issues a certificate if everything goes well, and you have a device object that is created in Azure AD. So here on the bottom you see this new device which Azure AD joined. You can see who the owner is, which is the user that just registered it. And you can also see that there's not yet an MDM set up for it, or it's not compliant because it's not yet joined to any MDM. But the device object exists. And the device now has a certificate, which it gets here. So this is the response, which basically gives you the certificate the thumbprint of the certificate and the certificate data. And it also makes some membership changes. So this is the changes to the local administrators group to add the correct security identifiers to there that Azure AD admins can log in on your laptop and have administrative rights. But the important part is the certificate here, which basically establishes a trust between Azure AD and the device, because Azure AD can recognize the certificate that it issued, and the device can prove that it possesses the key for the certificate by signing some data, for example. Then if you query the status of the device, it will say, hey, yes, I'm Azure AD joined, and I have this certificate that identifies my device. And in this case, we also see that the key provider for the certificate is the Microsoft Platform Crypto provider, and also that it's protected by a TPM. So what is a TPM? A TPM stands for Trusted Platform Module, and it's sometimes it's a separate processor, and sometimes it's integrated in the CPU, but it's kind of used as a sort of secure zone that you're not supposed to be able to extract cryptographic data from. This is also probably why it's a requirement for Windows 11, because they really are pushing for these hardware secrets being used instead of software secrets. So how does a TPM work? We have just created two device keys, so a transport key and a device key, and these are stored in the TPM somehow. I don't know exactly how it works. But the idea is that you can't extract these keys from there any longer. What you can do is use the keys. So the device itself can say, hey, I'm trying to use this key to do some cryptographic operation. Hey, TPM, can you please do that for me? And the TPM will sign whatever data you want, and then it will go on its merry way. And well, basically, you can use the keys, but you cannot steal them or use them somewhere else. There's a few caveats with that. A TPM doesn't protect against all attack scenarios. What the TPM protects against is like key extraction from a powered down stolen device. So if my laptop gets stolen while it's off, the TPM should protect its cryptographic data, especially if it's protected by a PIN. And it also prevents attackers from extracting the raw key data from the operating system level. What it doesn't protect against is, in some cases, like sniffing the connection between the CPU and the TPM, or, like I mentioned before, from actually using the cryptographic material if you have the correct privileges on the system that the TPM is in. So this is the important distinction. So even though the secrets are stored in hardware, it primarily protects against secret theft or accessing the secrets from the device while it's powered off. It doesn't prevent anyone from using the secrets if they actually have code running with high privileges on the machine. All right, so now we looked at how the device registration works. After you've registered your device, the user will sign in with their username and passwords on the normal Windows login screen, which in this case is the username password of the Azure AD account. And then Azure AD will issue a primary refresh token. Now, what is a primary refresh token? A primary refresh token is like a long-lived token which can be used to get other tokens. If you're familiar with Kerberos, it's kind of like a very long-lived ticket-granting ticket. So you can use this primary refresh token to request other tokens, which you can then use to sign in into Office 65 or whatever Azure AD joint service that you want. So how is this issued? First of all, in most of these token issue processes, you first have to get a nonce from Azure AD, because you have to sign some cryptographic data, and that usually is a nonce that you get from Azure AD, or it's called a challenge in this case. So it's just a post request, and you say, hey, please give me a challenge, so some piece of data that I can later use to use my cryptographic knowledge on. It's just a simple post request. And this gives you a nonce. So it's just a nonce, it's some binary data. It's encrypted. Azure AD can decrypt it. You yourself are not supposed to. So it contains some data, but you don't know what, and you also can't change it. So you can only use it in the further flow. Now, to request a primary refresh token, it sends some signed data back to the server. And well, you see a lot of things here. But if you're familiar with tokens, you can already see the EYJ here, which is kind of a hint that it's probably a JSON web token. And indeed it is. And in this case, you can see that it sends a request using a signed JSON web token, which contains the username and password of the user that is currently signing in. And it also includes the nonce on top of here. So it takes some data that it gets from Azure AD, it adds the username and password, and then it sends that back to the server. Then it gets a reply. And in this reply is our actual primary refresh token. So this is also like a blob of encrypted data. You cannot do anything with it. It's encrypted with keys that only Azure AD has, but you can use it to request other tokens. You also get an encrypted session key. And this is where the transport key comes in that we generated earlier. So the device has the transport key. It can decrypt the session key. And then the session key is the piece of information that it needs to actually use this primary refresh token. There's also some metadata in here, which says that the primary refresh token expires in 2 weeks. This is a lie. It actually is valid for 90 days. I'm not sure if they updated this already, but it says it expires, but it doesn't, or at least not as quickly as Microsoft tells you that it does. So in all this long flow of signing up and getting a primary refresh token, we have basically 3 important keys. So the key of the device certificate, the transport key, and the session key of the primary refresh token. And these are all stored in the TPM. And the operating system can use these keys, but it can't extract them from the TPM, even if it has the highest privileges. And using all these keys, the operating system can basically use single sign-on to sign in to any Azure AD resource. So let's see how we can interact with those primary refresh tokens. So the primary refresh token is a token that can be used for single sign-on. And if you're familiar with how Windows does single sign-on, you probably know that any application that is running on the system can request single sign-on data. So it can just say, hey, I'm trying to sign into this application. Can you do that for me? And that uses some RPC methods, or or some helper applications to make sure that this single sign-on can also integrate with third-party browsers like Chrome, which don't do this natively. But basically, here are some references that you can use to basically request single sign-on to any Azure AD connected resource, as long as you have some code running on the host. So the important thing here is this is all nice that it's protected by a TPM or whatnot, but if there's some untrusted code running on your system, that can just request tokens and just sign into anywhere it wants. So this example, I'm using 2 different systems. One is my attacker system and one is the victim system. And here I'm just requesting, like, okay, can I log in on outlook.office.com, for example, and so give me a nonce to use for signing in, and then Azure AD will give me a nonce, and then using that nonce on the victim machine, I can just say, hey, can you give me some magic data that allows me to do a single sign-on using this nonce? And it will happily give you some data back that I call the primary refresh token cookie. Basically, this is something that you can send to Azure AD and say, hey, I'm already signed in. Please just give me tokens instead of asking me to sign in again, because I'm using single sign-on. And if you use this, this token, so this JSON Web Token data to authenticate, then you can actually get some access tokens which allow you to, for example, read email via the outlook.office.com. So we can use the primary refresh token cookie, which is based on the original primary refresh token with the nonce, to actually sign in and get the access token that we need. And I'm doing this on my attacker system, so I'm not doing it on the victim system. But you can see that I can do the single sign-on, and I get a token which basically says, hey, I'm on a managed device, the device is domain joined, and it's in a known network. So it gets the data from the original device, which in this case was a hybrid Azure AD joined device, instead of my attacker device, which is obviously not joined to the corporate domain. So this is how you can use single sign-on to access Azure AD resources, as long as you have a session on the, or as long as you have code execution on the victim's machine. Now, of course, if you're an attacker, you don't want to rely on continuously having code execution on the victim machine to do your actions. So it would be great if we could somehow steal the data and have some persistence. So I did some further research together with Benjamin Delphi. Probably you know him as the creator of Mimikatz. And we actually looked at how the primary refresh token is stored. And we built some combination of Mimikatz and Rotools to actually steal the PRT from LSS. Now, I don't know how all that LSS magic works, but basically I know if you run Mimikatz with the right command, that it dumps the data from LSS, and that you here get the primary refresh token because it's cached in the memory of the LSS process. So that way you can steal the primary refresh token. One thing that this doesn't show you is the session key. So what's important to know is that the primary refresh token itself it's not really a secret. Every time you use single sign-on, the primary refresh token is sent to Azure AD. You can read it as a normal user. It's not supposed to be secret. But what is supposed to be secret is that session key. And the session key is needed to actually convert the primary refresh token itself in what I call the primary refresh token cookie, which allows you to authenticate. So let's have a look how how authentication with the primary refresh token works. On the left, you see the, as I call it, PRT cookie, which is a JSON Web Token. And on the right, you see the decoded version. If you're familiar with JSON Web Tokens, you already know that it basically consists of 3 parts. There's the header, there's the payload, and the signature. And on the left-hand side, you can see the header in red, the body in pink, and the signature in, well, kind of bluish. And if we decode this, we see that we see some fields in the header, which is one of this is the CTX field, which is what we call the context. And this is actually sort of a client nonce to make sure that every time you authenticate using the primary refresh token, it has a unique structure. This is important for later. And in this cookie, we also see a refresh token field. And this is actually the primary refresh token. So like I said, it's not a secret. You put your token in the field, and then you eventually have to prove that you also know the session key in order to authenticate with it. We also see the nonce. So that's a nonce that's requested from Azure AD. And on the bottom here, you see the signature of the JSON Web Token. So what it does is basically use the session key to compute the signature over the whole payload of the JSON Web Token. I made a little flow diagram for that. So this is starting from the scenario that that you don't have a TPM and everything is in software. In this case, what it does, it generates some random bytes, which is the context, which you see back here on the top right. And basically, using these random bytes plus the session key, it uses a key derivation function to create a derived key. So based on that context and the session key, you get a derived key. Then you put the primary refresh token in it, you put the nonce from Azure AD in it, and then you sign the whole thing using the derived key. And then you get your PRT cookie, which is a JSON web token, and that you can use to sign in. So if you have an implementation which uses software only, then you can basically steal the session key from LSS, and you can just take all this information to some other computer and basically have persistence over that. Of course, that's not what you want. So you want this to be protected by hardware. And in this case, we're looking at how the flow works with the TPM. So this is the same flow, but now it's also using a TPM. And in this case, we still generate some random bytes, and we want to use the key derivation function using the session key with that, but we don't actually have the session key. And with we, I mean the LSS process. So the LSS process has to ask the TPM, the separate crypto processor, to, hey, here's some random context. I know you have a key somewhere. Please give me a derived key from that. And that's what the TPM does. So you just generate this random context, and you give that to the TPM, and it gives you back a derived key. Well, with that derived key, you can actually compute the signature for this primary refresh token cookie, and then you can authenticate. Now, if you're staring at this for a while, you'll notice that, hey, there's some security flaw in here. The flaw is that there's not really any information that you cannot calculate beforehand in order to get your derived key. Because this primary refresh token is something you have. This nonce from Azure AD you can just query whenever you want to sign in. But these random bytes, you can just generate them wherever you want. So if you give an attacker like 5 minutes in a room with this TPM, it's just going to say, OK, I have some random bytes, give me a derived key. And if you do that 1,000 times, you have 1,000 unique combinations of random bytes, derived key, that work with the session key. So you don't even have to know the session key. You can just pre-calculate a lot of values, and then you can sign in forever with this primary refresh token. You can do that with Mimikatz. So in this case, it calls the correct crypto APIs, and you see that here it generates a random context, and it gives you a talk to the TPM, and then gives you the correct derived key. And with this combination of context and derived key, we can basically sign our own authentication cookies. So that's what I'm doing here with RoTools. And in this case, I'm authenticating, and I'm saying, hey, here is an existing cookie, which is probably not valid anymore. But I also have a combination of context and derived key. And you can use that combination to just recalculate the signature on the JSON web token, and then you get a valid authentication again. So this you can use indefinitely, and you can have a kind of persistence over this primary refresh token, and with that over the user's account. So the short version, if you're an administrator on a device with a primary refresh token, you can steal this primary refresh token and the session key if they are not stored in TPM. If they are stored in a TPM, you can still acquire many combinations of context and derived key that you can then later on use to create valid authentication cookies. This is a bit short version. If you want to read the longer version, including all the details, it's on my blog. And basically, as I blogged about this, Microsoft was like, this is kind of an issue, because of course the hardware protection of this key is now kind of redundant, because you don't even need the session key. So they changed this, and in August 2021, they released some Windows Update, which introduced some patches, which also broke the Mimikatz Cloud API functionality. It's still not working today. But the data is there in LSS, so if someone invests a lot of time in order to figure out exactly how that's stored, you can steal the PRT data again from LSS, but of course not the session key, which is in the TPM. And I did some analysis of how it is actually calculated post-batch. And if we look at the PRT cookie, we see a new parameter in here, which is the KDF version 2. So it probably hints us that there's a new way of calculating the correct key. And that's correct. So I did some reverse engineering of how exactly the new key is calculated. Basically, at some point it calls this encrypt key derivation function, which is used to derive a key from the context. And that takes some parameters in it. You can use a tool like API Monitor to see, like, hey, what are these parameters that it's actually sending to the TPM? So if you look at the memory at the time this function is called, you can see basically some of these buffers in which the information is stored. And there are 3 of them, and the one in the middle is the one we're interested in. So in this case, you can see that there's like a length of the data and the data type, and then a pointer to the actual data. Long story short, if we look at this buffer, that contains the context. And we see the length is 20 in hex, which is 32. And so it turns out that the context is now suddenly 32 bytes, where previously it was 24 bytes. So somehow the context got longer, while the context that we see in the JSON Web Token is still the same. And here are these 32 bytes. So I did a lot more reverse engineering, and eventually figured out that what they do is they actually don't use the context that they randomly generate, but they take a SHA-256 hash of the random context, which is these 24 bytes, plus the body of the JSON Web Token, to calculate a new context, and that they give to the TPM. So previously, they just used a random context and gave that to the TPM to calculate a derived key. Now they actually use a SHA-256 hash of the random context plus all the content of the JSON Web Token body. When I finally figured this out, I was very happy. And then I found out that I also could simply have read the documentation because they actually documented this change. So it just says in the documentation, if you have KDF version 2, you should use SHA-256 of the context plus the assertion payload, which is the body of the JSON Web Token. Oh, well, could have saved myself some time. But I once again created a scheme to kind of show how this now works. So once again, you get this nonce from Azure AD, and you have the primary refresh token. And this generates the body of the JSON Web Token. You also have the random bytes that we have. And if you take the SHA-256 hash of this, you get like the key derivation function context. That you send to the TPM, and then you get your derived key. And with the derived key, you can properly sign the final authentication cookie. And well, as you can see, this whole thing on the left is now required for the information to go through the TPM and get your derived key. So you cannot calculate these things in advance anymore, as the nonce that you get from Azure AD is only valid for like 5 or 10 minutes. So you will always need live access to the system in order to get this nonce, get the PRT, and then talk to the TPM to get the correct derived key. So this was fixed pretty nicely, and now you can no longer just pre-calculate whatever you want. And it was fixed as well, some CVE in 2020, and basically the new method prevents you from pre-generating all these combinations that you need. And they also smartly prevented you from downgrading from the KDF version 2 to KDF version 1. That's the first thing I tried, of course. They also specify somewhere inside the primary refresh token, I assume, because it's encrypted, which method you used to first request the PRT. So when you send that request to Azure AD, to get a PRT, you can also indicate, hey, I support KDF version 2, and then they issue you a token which has that KDF version 2 property probably stored somewhere in it, and you can no longer use the version 1 to authenticate with a primary refresh token that was requested from a system that supports the new way of working. So this was fixed. That's great. There were some other things that I looked at. And for that, we go back to the device join scenarios. Because this whole primary refresh token downside stealing has some downsides. Of course, you need it to be admin. You need to dump LSAS. That's quite noisy, especially with EDRs. And of course, they fixed this whole thing, so it doesn't work anymore. And last of all, if the blue team notices that your device was breached, they will probably disable it, and that means that your primary refresh token will also no longer work if you stole it from the device. So I thought, okay, what if we combine two pieces of knowledge? So first of all, we know how to get our own primary refresh token by registering a device. And we also know that we can get access tokens if we have code execution on a machine by using single sign-on. So what if I register a new device using a single sign-on token? Then I don't need to know any secrets. I can just do this. So I initialize the single sign-on flow. First I request the nonce on my attacker hosts, and then I run row token, so I get a single sign-on cookie. And then I actually authenticate to Azure AD in order to register a device. So what you see here is I used it's some random GUID, but basically this means I'm authenticating to the device registration service, and that gives me a token that allows me to register a new device. And in this case, I just got this token by using single sign-on. So with this authentication data, I can register a new device. I wrote some code in Python to do this. You can also do this with AAD internals, and I slightly adapted the code from it. And AAD internals was written by Nestor, which is also sitting here. So thanks for AAD internals. It's a great toolkit. So you can use that or this Python code to register a new device, and that basically issues a certificate for your device because you just registered it with Azure AD. And once you have that device certificate, you can also get a primary refresh token if you know the credentials of the user. So we only need the credentials of the user to register the device. No, we don't need any credentials to register a device because we're using single sign-on. And if you have credentials of the user, you can also get a primary refresh token and the session key. And in this case, the session key is not actually encrypted with hardware, of course, because we're just using our own Python script. And if we use this primary refresh token and session key to sign in, then we get an access token for whatever we want to access. And there are some interesting things in that. So if you decode this access token, you will see some authentication claims. And in this case, you see the PWD claim, because we used the password to authenticate, the RSA claim, because we did it using a primary refresh token, but also the MFA claim. And if you look, if you recall from previous steps, I didn't actually need MFA for the user at any point. Now it turns out that if you use a single sign-on token, which was used with MFA, so the primary refresh token will include the MFA claim because the user did MFA in the past. And if you use that to register a new device and then get a primary refresh token for the same user, the MFA claim is actually included. So even though we never did any MFA for the user, we still get that claim in the primary refresh token that we kind of stole from the device. So to summarize that, we can request a single sign-on token, which contains an MFA claim. And if we then use that to register a new device, the issued PRT will also have that MFA claim. And in this case, we only require the password. But if you're using ADFS, you could also use single sign-on with NTLM or Kerberos to get a PRT, and you wouldn't need the user's password at all. So in this case, we had a free MFA upgrade, and we now have persistent access to the account using a primary refresh token. There are some upsides and downsides to this. So we registered a new device, which is great because it's a separate device from the old device, and if the breach is noticed, they could disable the old device, but our new device that we registered using the old device is still working. Downside is that you will need permissions to register devices in Azure AD, which is not always allowed. And of course, you also have some restrictions sometimes, like what I mentioned with bring your own devices. So we probably couldn't enroll this device in Intune if they restrict which devices you can enroll. So I wanted to fix this last one because it's kind of annoying. So how about work bypassing these Intune restrictions? If you look at the device registration flow and the Intune registration flow, Windows presents that as like one flow because you can just click join and everything is magic. But it's actually two separate steps. So the device registration process registers the device in Azure AD, and then it's a separate process to register the device in Intune. Now, if you're restricting which devices can be registered in Intune, the second step will fail because you're not allowed to register a non-corp device in Intune. And Windows will then automatically also revert the first step, so it will delete the device back from Azure AD, and it will give you some error. Of course, if you do this manually, you can still do the first step, so you can register a device regardless of whether you're allowed to enroll into Intune or not. But this won't necessarily give you a lot of things, because then if you register your own device and don't register it in Intune, you will not get the compliant device claim, which is what we wanted to bypass with the conditional access. So I looked at this process, and I noticed that if I had a device which was registered in Intune using Autopilot, even if I wiped and reinstalled it, the same device object would be used to register my device in Azure AD. I was wondering, so how does Azure AD actually know this is the same physical device? Does it have some magical link to know that this device is the same from the device I installed previously? So I started looking into this, and for that we go back to the registration request, which we talked about earlier. So we have all these properties and these certificates and keys. And what's interesting here is this device ticket. And well, the device ticket, it's a kind of a ticket for your device. And what I noticed is if I did subsequent registration requests using the same blob of binary data as a device ticket, it would keep overwriting the same device in Azure AD. So somehow this device ticket is used to identify a unique combination of hardware. So if I reuse this, it would keep working. It did seem to expire after a certain period of time, so I couldn't use it like 2 weeks after, but within a few hours it would keep working. So what is this exactly? So I looked at the registration flow, and which is quite annoying because this is a web-based interface, and if you do things from a web-based interface, it uses WinRT APIs, and they are based on COM. So basically, if I click on a button, it will randomly spawn some process somewhere else, and then it will do things in there, which is annoying to debug, because if I look at one process and it just spawns something somewhere else, then I have to switch to that process. But I eventually got it working, and what it does is it spawns, it uses DLL host to launch dsreg.dll, and that contains the actual registration logic. So basically, this dsreg.dll is responsible for doing all this registration stuff and also for getting the device ticket. So I reversed this a little bit, and I don't know if this is readable for you, but basically it constructs some classes here. And if we just Google for this all long class combination, we find some Microsoft documentation for the online ID service ticket request class. So this is apparently just some Windows APIs that you can use to request tickets. And it allows an app to specify device with policy, blah, blah, blah. Basically, you can use this to get tickets for the user or for the device, as it seems. So in conclusion, it appears that your device has its own Microsoft account, separate from any Azure AD join function. Your device has its own account. And when it needs to authenticate to Microsoft for updates or whatever, it uses this account identity. And these device tickets are actually cached in the registry, in the current user registry hive. I don't know why, but basically they're in there. And they're encrypted with TP API, but they're encrypted with the machine context. So even if you have the tickets of another user, you can still decrypt them because they're tied to the machine. So I wrote some simple PowerShell code, which imports TP API and basically decrypts those tickets. And then you can just decrypt all the cached tickets that are on the host. And here at the bottom, we see one of the tickets, which is for the enterprise registration.windows.net, which is the domain that we use for device registration. And here you see like the device ticket, which starts with T equals and then some encrypted data. And if you base64 encode this piece of string, and then you get your MSA DDID thing that you can use during device registration. So somehow the ticket that's used for device registration that allows you to override the device is stored locally in the registry and can be queried by your current user. So that's interesting. So you could steal those tickets and override the device. But these tickets are usually old and they may not always be there. So I did some further reversing and just constructed exactly which API calls were needed. And eventually just found the GUID and the registration endpoint. And then if you read the documentation, you can write some very simple .NET application, which actually requests a ticket. And I was very surprised that it actually worked. But if you run this code, you just get a new ticket, and that ticket identifies your device. If you do this from any low-privileged user, you get the device ticket, which once again allows you to override the device. So in this case, I'm using the register device function again to register a new device. But this time I'm using the device ticket that I just queried on the host to say, hey, what instead of registering a new device, you simply override this old device. And then, well, it works. So you see that we get a certificate with a common name, which is a GUID, but it matches the GUID of the device that we were running the code on earlier. So we actually overrode the actual device in Azure AD using only single sign-on data and using a ticket that the low-privileged user account could query. And the nice part is the device retains its original properties in Azure AD. So it still thinks that this device that we just overrode and we stole all the credentials from is still very much compliant, and it's managed by Intune. And if we try to sign in using our stolen tokens, it will also say, hey, this device is compliant and it's Azure AD joined. So long story short, if you have code execution, you can request a device ticket, and then you can register a new device and just override the old device. Of course, when you register a new device, you create the key pairs yourself. So they're no longer protected by a TPM, but you just have the device identity using the new secrets that you possess yourself. You don't need to steal the PRT from the TPM anymore, and you don't need any administrative privileges at all, because everything can be queried from a low-privileged user. Additionally, any user in the tenant can override the device, so you don't need to do this using the user that's legitimately tied to the device. You can just request the device ticket using one user, and then override the device using another user. This device ticket stays valid even after you wipe the device. So if in the morning I request a ticket, in the afternoon they find out this device was compromised, they wipe it, reinstall it, and give it to a new user. In the evening, I could just use the same ticket again and overwrite the device again. And what's also fun is that the identity that creates the new device becomes the owner of the old device. This also means that it can view any BitLocker keys that were stored in Azure AD. So if I have physical possession of the device, I could also decrypt it or do whatever. It basically is also a privilege escalation to administrator, because we're doing this from a low privilege user, and we can access the BitLocker keys, which are normally not readable by low privilege users. And the best part maybe is that because we don't actually register the device in Intune, the old device will keep reporting to Intune that yes, it's compliant with everything you ask, and Intune will actually keep updating the compliancy status of the device that we now own. So, just to sum up a bit, because I think I'm running out of time. If we combine all of this, then if you have like code execution for a few minutes on the system of the victim, we could use single sign-on to register a new device. We could also use the device ticket to override the current device, which gives us access to the primary refresh token, which gives us access to the keys that are required to use the primary refresh token. We also get the MFA claim attached to our primary refresh token, and we also get the compliancy claim because we overrode the original compliant device. So this bypassed MFA, the hardware security, and also the need to dump LSS or even administrative privileges. I'm going to skip over this. So I disclosed this to MSRC, the registration used single sign-on in December 2020. That was fixed in September 2021. So now you can no longer use a single sign-on token to register a new device, but you need to use like a fresh token. The overriding of a device was reported in May 2021, and they actually patched that last month via Windows Update. So they made some changes to the registration process. I don't know exactly what, but they also assigned a CVE for that. So this should also no longer be possible. This one I'll have to skip because we're out of time. So to conclude, the secrets in hardware were not always very efficiently protected. Basically, you could just, well, pre-calculate everything you needed to need them. You could create a primary, you could get your own primary refresh token just by registering a new device instead of trying to steal it from the old device. And you could take over the whole device identity by simply requesting a ticket for the device. And there's also this thing with Intune admins that could bypass MFA, but I'll leave that for next time. So this should all be fixed now. Just if you patch your endpoints, the cloud is already patched, of course. Lastly, all the tools that I used are based on the Road Tools framework. I still have to make some changes before I push these scripts publicly, but they will be open source. I do have some stickers here, so if you want some nice Road Tool stickers, just go to me after the talk, or if you see me walking around. And if you have any questions, I'm not sure if we still have time for those, but you can always ask them via Twitter or just send me a mail. Thank you.